GenAI and MLOps Part 4. This episode has 11 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. LLM Gateway. Mach 50 Focus. LLM Gateway. How would you build an internal gateway that handles off-prem token budgets, prompt templates, model fallback, audit logs, and provider abstraction? Here's a strong way to approach it. Build a proxy service between applications and model providers. It authenticates callers, maps them to teams or projects, enforces rate limits and token budgets, injects approved prompt templates, and routes to configured models. It should abstract providers such as Vertex AI, OpenAI, Anthropic, or self-hosted VLLM so applications do not hardcode provider logic. Add retries, timeouts, circuit breakers, fallback rules, audit logs, cost attribution, and dashboards. For safety, restrict which teams can use which models, prevent logging secrets, and require approval for high-risk tools or external data sharing. Nice. Let's continue. Question 2. Prompt engineering. Mach 50 Focus. Prompt life cycle. How would you version, test, review, deploy, and roll back prompt changes like application code? Here's a strong way to approach it. Store prompts in Git with owners, version numbers, changelogs, and environment-specific configuration. Every prompt change should run against a regression dataset with expected behavior, groundedness checks, safety checks, latency or cost checks, and human review for high-risk flows. Deploy prompts gradually using feature flags or config rollout. Track prompt version in every trace or log, and keep old prompt versions available for rollback. The key interview point is that prompt changes can break production like code changes, so they need review, tests, rollout, observability, and rollback. Great. Moving on. Question 3. LLM evaluation. Mach 50 Focus. LLM evaluation. How would you design automated and human evaluation for answer quality, groundedness, toxicity, latency, and regression testing? Here's a strong way to approach it. Use layered evaluation. Automated tests should include fixed golden questions, expected source references, rubric-based LLM as judge scoring, toxicity or safety checks, hallucination or groundedness checks, latency, token cost, and exact match tests where applicable. Human evaluation should review samples for correctness, tone, safety, and business usefulness, especially for ambiguous or regulated use cases. Track scores over time and block deployment when a prompt or model change regresses beyond thresholds. Keep evaluation data versioned so results are comparable across releases. Alright, next question. Question 4. LLM security. Mach 50 Focus. Prompt injection and data leakage. How would you protect an LLM application from malicious input, unsafe tool calls, PI leakage, and retrieved document injection? Here's a strong way to approach it. Treat user input and retrieved documents as untrusted data, never as instructions. Use strong system prompts, clear delimiters, content filtering, tool allow lists, schema validation, and permission checks outside the model. Do not give the model broad credentials. Tools should use least privilege and require confirmation for destructive actions. Redact PI or secrets before prompts and logs. Restrict which documents can be retrieved by user or team authorization, and monitor for injection patterns. The strongest control is not a clever prompt, it is limiting what the model can access or do if the prompt is bypassed. Let's keep going. Question 5. LLM deployment. Mach 50 Focus. Self-hosted versus managed LLMs. How would you choose between Vertex AI or Gemini, OpenAI API, and self-hosted VLLM or Llama on Kubernetes? Here's a strong way to approach it. Use managed APIs such as Vertex AI or Gemini or OpenAI when you want fast adoption, strong model quality, low platform operations, and managed scaling. Use self-hosted VLLM or TGI or Llama on Kubernetes when data residency, cost at scale, latency control, custom models, or offline or private operation matter enough to justify GPU operations. Compare model quality, token cost, page 95 latency, throughput, privacy, compliance, operational burden, GPU availability, autoscaling, and fallback options. Many production platforms use both managed APIs for high-quality general tasks and self-hosted models for private, high-volume, or cost-sensitive workloads. On to the next one. Question 6. LLM fine-tuning. Mach 50 focus. Fine-tuning versus RAG. When would you fine-tune an LLM instead of using RAG or prompt engineering? And what operational risks would you manage? Here's a strong way to approach it. Use prompt engineering for behavior or formatting changes when the base model already knows the task. Use RAG when answers need current, private, or auditable knowledge from documents. Use fine-tuning when you need the model to learn a repeatable style, domain-specific classification, extraction format, or task behavior from many examples. Fine-tuning adds risks: dataset quality, bias, overfitting, model versioning, evaluation, rollback, cost, and retraining. It is not a good way to inject frequently changing factual knowledge. RAG is usually better for that. Good. Here's another one. Question 7. Machine learning basics. Mach 50 focus. Machine learning fundamentals. Explain supervised learning, unsupervised learning, and reinforcement learning with practical examples. Here's a strong way to approach it. Supervised learning trains on labeled examples, such as predicting churn from customer records or classifying incidents as high or low priority. Unsupervised learning finds patterns without labels, such as clustering customers, detecting anomalies, or reducing dimensionality. Reinforcement learning trains an agent to take actions and receive rewards or penalties, such as game playing, robotics, or policy optimization. In interviews, connect the learning type to the data available. Labels imply supervised. Hidden structure implies unsupervised, and sequential decisions with rewards imply reinforcement learning. Nice. Let's continue. Question 8. Machine learning workflow. Mach 50 focus. ML life cycle. Walk through the end-to-end machine learning life cycle from problem framing to data collection, training, deployment, monitoring, and retraining. Here's a strong way to approach it. Start with problem framing. Define business objective, prediction target, success metric, constraints, and risk. Then collect and validate data, engineer features, split train or validation or test sets, train candidate models, evaluate offline metrics and business relevance, package the model, register it with lineage, deploy through canary or shadow or A or B if needed, and monitor latency, errors, drift, data quality, prediction quality, and business KPIs. Retraining should be triggered by schedule, new labels, drift, or performance degradation, but production promotion still needs validation and rollback controls. Great. Moving on. Question 9. Feature engineering. Mach 50 focus. Feature engineering. What is feature engineering? Why does it matter? And how do you avoid training serving skew? Here's a strong way to approach it. Feature engineering means transforming raw data into useful model inputs, aggregations, encodings, normalization, time window features, text embeddings, missing value handling, and domain-specific signals. It matters because model quality often depends more on useful features than algorithm choice. To avoid training serving skew, reuse the same feature definitions in training and inference. Version features, validate schemas, monitor freshness, and use a feature store or shared transformation library where appropriate. Always record feature version and data time range in model lineage. Alright, next question. Question 10. Model evaluation. Mach 50 focus. ML model evaluation. How would you choose metrics such as accuracy, precision, recall, F1, ROCOC, RMSE, and business KPIs? Here's a strong way to approach it. Choose metrics based on problem type and business cost of errors. Accuracy is useful only when classes are balanced and errors have similar cost. Precision matters when false positives are expensive, such as unnecessary fraud blocks. Recall matters when false negatives are expensive, such as missing fraud or incidents. F1 balances precision and recall. ROCOC helps compare ranking ability across thresholds. RMSE or may fit regression problems. Always connect technical metrics to business KPIs such as revenue, risk, support tickets, latency, or user experience. Let's keep going. Question 11. Model reliability. Mach 50 focus. Overfitting and underfitting. How do you detect overfitting or underfitting? And what actions would you take? Here's a strong way to approach it. Overfitting means the model performs well on training data but poorly on validation or production data. Detect it through train validation metric gaps, unstable cross-validation, and poor generalization. Fix it with more data, regularization, simpler models, dropout, pruning, early stopping, or better validation splits. Underfitting means the model is too simple or lacks useful features, causing poor training and validation performance. Fix it with better features, a more expressive model, longer training, less regularization, or improved data quality. On to the next one. That wraps up this episode. Nice work practicing, and see you in the next one.